Let's solve this question. What they are saying is that find the eigenvalues and eigenvectors for the following matrix. So let's find eigenvalues and eigenvectors for this matrix. What do you need to do? You can just you can just subtract lambda from the diagonal, and then you can solve for the determinant to find the eigenvalues. So this will be 3 minus lambda, this is minus 2, this is 1, then this is 0 minus lambda, which is minus lambda only, right? Okay, so the determinant has to be 0. Then this will be 3 minus lambda into minus lambda, and then minus of minus 2, which means plus 2, right, equal to 0. So from here you can calculate the value eigenvalue. So let me go to the next page, or maybe I can just solve here only. So if you solve for the lambda, then you will be getting something like this. It will be minus lambda into into 3, it will be minus 3 lambda, and then lambda square minus 3 lambda plus 2 equal to 0, and then you need to factor it. So factor it such that you get 3 by subtraction or division, subtraction or addition, and you get 2 by the multiplication. So I think minus 2 and minus 1 should be the factor. Minus 2 lambda plus 2 equal to 0. So from here you can take the lambda common, and then it will be lambda minus 1, and then from here if you take the 2 lambda common, minus 2 lambda common, then it will be lambda minus 1, right? So it will be minus 2 common, then it will be lambda minus 1. So lambda minus 1 into lambda minus 2 equal to 0. So lambda equal to 1 and lambda equal to 2. So 1 and 2 are two answers. Let me quickly check. Yes, 1 and 2 are the two answers. Now what you can do, you can find the eigenvectors also, right? So let me find the eigenvectors for this particular matrix that we have. Let's just find the eigenvector for the lambda equal to 1. Okay, for lambda equal to 1, if you find the eigenvector, it will be 3 minus 1 minus 2 1 and then minus 1, which means the matrix which we get is basically 2 minus 2 1 minus 1, and we need to solve for bx equal to 0, right? We need to solve for bx equal to 0. Now if you just observe, I think you can make one of the row as 0, because there has to be one free variable, that is for sure. So you can make one of the row, I'm 100% sure, like if you try to make this as 0, it will automatically be 0, because every eigenvalue, whatever the eigenvector it has, it must be having the free variable, because for corresponding to every eigenvalue, there is not just one eigenvector, there are infinitely many eigenvectors. So from here I think let's not do it. I mean, if you want you can do it, maybe 2 times of this, and then subtraction of this will make it 0. But yeah, from here you can say that x2 equal to k, and x1 will be, you can say that 2x1 minus 2k equal to 0. So x1 will also be k. So x1 and x2 both are k, right? So you can get the final answer, which is something like this. So for lambda equal to 1, you get this as final answer. Let us now solve. Okay, so let's now solve for lambda equal to 2 also. Now for lambda equal to 2, we will be having, this is 3, then it will be 1, and it will be minus 2, right? So 1 minus 2, 1 minus 2. Okay, so it will be 1 minus 2, 1 minus 2, right? Now this is let's suppose a matrix A minus lambda I, or you, if you want, you can call it B, and then if you solve for the x1 x2 will be, let's suppose, k, and x1 will be, it will be x1 minus 2x2, I think it will be 2k, right? Okay, so finally x you got is basically 1 2. So this is the x you got. So I hope you understood that for lambda equal to 1, we got this vector, and for lambda equal to 2, we got this eigenvector. So let me probably write both the eigenvectors here. Maybe for lambda equal to 1, you got eigenvector that you got is basically this one, which is x equal to k 1 1, and for lambda equal to 2, you got some eigenvector which is something like this. Eigenvector which is x equal to k 1 2, right? So these are the two eigenvectors we got for lambda equal to 1 and for lambda equal to 2. Now can you notice one thing, which is that these two eigenvalues are definitely not equal, right? I mean, this is 1 and this is 2. Then these two eigenvectors that you have are definitely not linearly dependent, because of the statement that we have already proved, right? Or we have already seen that eigenvectors from different eigenvalues are linearly independent. Now these are the eigenvectors from different eigenvalues, right? So that is why these two eigenvectors are linearly independent. Why? Because these are from different eigenvalues. I hope that is okay to everyone. I mean, this is just to verify you, or like although we have already proved it, but anyway, like proof is not important. I just wanted to give you some example where I just show you that okay, these are the two different eigenvalues, and you in fact have linearly independent eigenvectors, right? Let's solve more examples probably, and then let's just see what is happening. So let's solve for this. If you solve for this, then what you can do, this will be 3 minus lambda 1 0, 3 minus lambda, determinant equal to 0. And now if you solve for the determinant, it will be 3 minus lambda square minus this is 0, right? 1 into 0 is 0, so equal to 0. So from here you can say lambda is 3, right? So since it is power 2, that's why I'm just writing it 2 times. Okay, lambda equal to 3 comma 3. Like although lambda is just 3, but I'm writing it 2 times because roots are repeating. Okay, this is called repeating roots basically for the polynomial. So basically it means that if lambda minus 3 square is 0, then it means lambda is actually coming 2 times 3. If it is power cube 0, then I will write 3 times. I mean, although it is just one lambda, but I will just say that these are the 2 lambdas, okay? And both are same. So basically I will say that this is lambda 1, this is lambda 2, and lambda 1 and lambda 2 are equal. Okay, if it is repeating, then I will say that okay, lambda 1, lambda, these are the 2 lambda. If it is repeating 2 times, I will say 2 lambda. If these are repeating 3 times, I will say 3 lambda. I hope that is fine. Now let's just find the eigenvector corresponding to lambda equal to 3, right? So like this is the matrix, and if you just find out a minus lambda I, then this is 0 0 1 0 0. Okay, this is 0 1 0 0, yeah. So now if you solve for a bx equal to 0, so let's just call it b, or maybe a minus lambda I, and then you can say that okay, x2 is 0, x2 is k, x2 is k, and then okay, sorry, okay, yeah, this is interesting. Can you just tell me what is the free variable here? The free variable here is not not x2, it is actually x1, right? So x1 is a free variable, so let's just keep this x1 is equal to k, and then if you keep the x1 equal to k, then x2 will be minus k, right? Because sorry, x2 will be 0. From this equation you can find out x2 as 0, right? So finally x will be k into 1 0. So this is your x that you are getting from for the lambda equal to 3 comma 3, which means even though the lambdas are repeating, now listen here carefully, even though the lambdas are repeating, these are the 2 lambdas, right? I mean lambda 1 and lambda 2. So corresponding to these 2 lambdas, I'm just having one eigenvector. Okay, I'm not considering the multiple of eigenvectors, so just one eigenvector 1 0 I'm considering. I mean what I mean to say that corresponding to two eigenvalues lambda 1 and lambda 2, which are equal actually. So corresponding to the equal eigenvalues, I am getting just one linearly independent. See, earlier this was different, right? So lambdas are different. Lambda is equal to 2 here, lambda equal to 1 here. So if lambdas are different, I am getting definitely two different eigenvectors. That is for sure, right? Because of the statement that we have seen. See, the statement itself is saying, where is that statement? That eigenvectors from the different eigenvalues are linearly independent. So if these are the different eigenvalues, then these are definitely linearly independent, right? If these are the different eigenvalues, then definitely linearly independent. That's what a statement says. But here I have the same eigenvalues, right? And then what I'm getting is just one eigenvector. I mean the linearly dependent eigenvector. Basically these are not two eigenvectors I'm getting. Two linearly independent I'm not getting. Well, let's just see. Okay, I know you might get confused here, but don't worry, it will get clear with more examples. So currently I just want you to observe one thing, is that if lambdas are different, then you get the different eigenvectors. That is for sure. If lambdas are same, then in this case we are getting the same eigenvector. But can we get the different eigenvectors? Let's just see. Okay, so here I'm getting the same eigenvector, but let's just see if lambdas are different. If lambdas are same, then also can I get the different? Okay, so let's just be with the examples, and then you will get to understand what I mean to say. So let's just solve for this particular matrix, the eigenvalues and eigenvectors. So let me just solve it. Maybe I can go to the next page, and then it will be minus lambda, it will be minus lambda, it will be minus lambda. Let's just expand with respect to this particular column, right? Because these are the zeros. So if you expand, this is plus minus plus, plus minus plus, minus plus minus, plus minus plus, right? So it will be plus. Now let me quickly expand with respect to this 4 minus lambda, or maybe I have the answers on the next page. Yeah, so if you solve for this determinant, then I have the answers, which are basically 6, 4, 4. Okay, so these are the answers that that we already have. Which means that if you solve for the lambda, you are getting something like this. You might be getting something like this, which is lambda minus 4 square equal to 0. Since the 4 is repeating 2 times, that's why I'm getting 6, and then I'm just writing 4 2 times. Why? Because 4 is repeating 2 times. 6 is just repeating 1 time, that's why I'm writing it 1 time. Okay, so I got 3 lambdas. Out of that, two lambdas are same. Okay, I hope that is fine. Now let's just do one thing. Let's find out the eigenvectors corresponding to 6. Let's find out the eigenvectors corresponding to 4. And then let's just see what is happening there. For lambda equal to 6, for lambda equal to 6, you need to calculate the eigenvectors, and for lambda equal to 4, you also need to calculate the eigenvectors. So let's just calculate for lambda equal to 6. Now what you need to do, you need to subtract 6 from the diagonal, and then you need to solve for bx equal to 0. I think we can solve it. It will be minus 1, minus 1, 0, minus 1, minus 1, 0, and then, okay, let me just do it. Minus 1, minus 1, 0, minus 1, minus 1, 0, and then 1 by 3. So maybe you can multiply by 3 in this equation. This will be 1, minus 1, and then this is, since it is minus 2, you are multiplying by 3. That's why it will be minus 6, right? So that's how you can say that, okay, this is 0, 0, 0. And now you need to make, since these two rows are same, so you can directly say that this row is 0, because after the subtraction you will anyway get all the rows are 0, all the values in this row are 0. And then if you just compare these two, then maybe you can say, if you add these two, right? If you add these two, then you can just say that, okay, okay, sorry, let me do one thing. Let me probably, not modify the same matrix. Let me just modify after the rewritten. So that's what you got, and then you can get this matrix, right? You can get this matrix by adding the rows, and then let me just minimize this. So let's start from here. Sorry for the lack of space. We need to do all of this, right? Okay. So, and then you can say that from here you are getting, this is 1 minus 1 minus 6, this is minus 1 minus 1 0. So maybe you can add or both of this. This is minus 1 minus 1 0, and then 0, and then 0 0 0 you can write at the end. It will be 0, it will be minus 2, it will be minus 6, and then 0, right? So I think these two are pivot, and then you can easily solve for this. So how to solve? I think you can say that x3 is free variable, which is k. X2 and x3 are related like this, like x2 will be 3k, right? So it will be 6k, so minus 3k. So x2 will be minus 3k, and x1 will be x1 equal to minus x1 equal to, I think, x2. So x1 and x2 are differing by minus symbol. So x1 you can say equal to 3k. So anyway, finally you got a vector, which is basically x1 is 3, this is minus 3, this is 1, right? So finally you got a vector which is eigenvector for corresponding to lambda equal to 6, which is 3 minus 3 1. Let me check the answer. Yeah, 3 minus 3 1, right? Easily you can get this eigenvector. Now we got two eigenvalues, like one is 6, another one is 4, and 4 is repeating 2 times. So let's just see the eigenvector corresponding to 4 also, right? So let's calculate the eigenvector lambda 2 corresponding to 4. 4 is repeating 2 times, that is perfectly fine. It's not an issue, but let's just do it, okay? So if you do it, then probably let me do it quickly. This will be 1, minus 1, 0, minus 1, 1, 0, and then you can multiply by 3. It will be 1, minus 1, 0, right? Okay, this is 0, 0, 0. Now you notice here, I think you can add both of these rows, and then this will be 0. And since okay, these two rows are same, so that's why this is also 0. I hope you got it, right? Okay, let me rewrite it maybe. So you can make two rows as 0 here, which means these two are actually 0. These two rows are actually 0. So you will be getting 0, 0 here, 0, 0 here, right? After the elementary row transformation, you can easily get it. So you can notice that x1 is only the pivot. So x2 is, let's suppose, s, and x3 is, let's suppose, t. So x1 will be same as x2, which means it is s. So the final vector you got is x1, x2, and x3 SST, right? So this is the final eigenvector corresponding to 4. So let me write it. Lambda 2 equal to 4 4, and corresponding eigenvector that we got is SST. So SST means you can rewrite it in this form, like you can make s equal to 1 and everything else at 0, so it will be 1 1 0, and then you can make t equal to 1 and everything else at 0, so 0 0 1, right? Okay, great. So corresponding to lambda equal to 4, you got these set of eigenvectors. I mean here the set of eigenvectors are actually 2. I mean the linearly independent eigenvectors are 2 here, right? See, earlier also we got the many, again, this is not just one eigenvector, these are the many eigenvectors, but linearly independent eigenvector is just one, right? So see, if this lambda is just repeating one time, so there is just one lambda, then you cannot get more than one. I mean more than one linearly independent actually you cannot get if there is just one lambda. Okay, so anyway, I will talk about it later. But we already know one theorem is that if lambda 1 and lambda 2 are not equal, then the corresponding eigenvectors are linearly independent, right? So see, this 6 and the next one, which is 4, these two are not equal. That's why this is 3 minus 3 1, and here 3 minus 3 1. This was earlier for lambda equal to 6, and here you got you got this set of eigenvectors, right? You can multiply by k here. You can pick any eigenvector from here. Maybe I can go to the next page. See, lambda equal to 6, you got k into 3 minus 3, k into 3 minus 3 1, 3 minus 3 1, and for lambda equal to 4 4, you got I think SST, which means you got 1 1 0 plus 0 0 1. You got these two eigenvectors. Now you pick any eigenvector corresponding to lambda equal to 4. You pick any eigenvector. Maybe you can just put s equal to 1 and t equal to 1, right? You pick any eigenvector, and then I think it will be 1 1 1. You pick any eigenvector here. This is 3 minus 3 1. These two eigenvectors can never be linearly dependent because lambdas are different, right? If lambdas are different, then they are definitely linearly independent. That is for sure because of the statement. But if lambda is same, then if the lambda is same, there is just one more observation that I want to make using those two examples, like just the recent two examples. If lambda is same, then I can get two. If lambda is repeating 2 times, I can get 2 linearly independent eigenvectors. If lambda is repeating 2 times, see, if lambda is repeating 2 times here also, see, in this example also, I think lambda was repeating 2 times. If you notice that lambda was repeating 2 times. If lambda is repeating 2 times, but in this case, I just got one linearly independent only, like, let me not repeat linearly independent again and again. But yeah, if here also lambda is, you are having 2 lambdas, I mean, lambda is repeating 2 times, still just one eigenvector you got, right? But here in this example, lambda is repeating 2 times, still you got two linearly independent eigenvectors. So basically, let me just summarize something that I want to actually emphasis on. Let me just summarize something. If lambda 1 and lambda 2 are not equal, then corresponding eigenvectors are linearly independent. That is for sure. Corresponding eigenvectors are linearly independent. Okay. If lambda 1 and lambda 2 are equal, which means it is repeating 2 times, 3 times like that. Okay. I mean, both 4 and 4 are equal. I think we have seen one example, and 3 was the one, another example, 3 and 3 are equal. In that case, you can get, if it is repeating 2 times, then you can get either one linearly independent or 2 linearly independent. Okay. Then, how should I write here? Okay. If lambda is repeating 2 times, then we can get either one or 2 linearly independent eigenvectors. Okay, let me just give you one example. Maybe you will be more comfortable after this example. Let's suppose I get some characteristics equation, which is, let's suppose, lambda minus 1 power 2, lambda minus maybe let's suppose 5, lambda minus let's suppose 7 power 3, something like this. This is one characteristic equation that I got equal to 0. Okay, which means lambda equal to 1 is repeating 2 times, lambda equal to 5 is repeating 1 time, lambda equal to 7 is repeating 3 times. Now let me just ask you the question that number of linearly independent eigenvectors that you have in this case, total, okay, will be, let's suppose option A is saying at least let's suppose 6 eigenvectors, 6 linearly independent eigenvectors, at least 6, okay. Option B is saying at most 6. Option C is saying exactly 6. Option D is saying that, okay, at least 3, right? At least 3. Now let me know which of the following option is correct. So this is a MSQ question. MSQ means multiple answers could be the, multiple options could be the answer. So this is a MSQ question. MSQ means that multiple options could be the answer. Just let me know that which of the following are the correct answers, okay? Maybe there is just one answer, maybe there are 2 answers, maybe there are 3 answers. Just let me know in the next video. I mean, just comment it out and we will solve it in the next video. So, I mean, that's the easy question, but it is very important to understand that what I conveyed in this particular video, okay? So that's why I'm putting this question. See, just to repeat it out, that if lambdas are not equal, then you must get corresponding eigenvectors linearly independent. If lambdas are equal, then you may get or you may not get, okay? I mean, you may, if these are the 2 lambdas which are actually equal, then you can think that, okay, there may be 2 linearly dependent eigenvectors or maybe just one, right? Or maybe just one. So basically, if lambdas are not equal, then you will definitely get 2 linearly dependent eigenvectors, or however lambdas they are. If lambdas are equal, then you may get linearly independent, 2 linearly independent, or you may get just one linearly independent, okay? So just try out this question. Thank you.